Welcome back. And I'm continuing with what I explained to you, the electric field, the beautiful concept, and we derive the electric field for a positive charge Q at a distance r away from it. Okay. The value will be equal to E is equal to 1 upon 4 pi epsilon naught epsilon r into capital Q upon r square. Oh, a new thing, epsilon r I have introduced. Epsilon r is called relative permittivity. Okay, and it is a pure number because it is the ratio of the permittivity of a medium divided by the permittivity of free space, or A. So epsilon is equal to epsilon r into epsilon naught. Okay, it's only up to this point just to introduce you the value of epsilon r, but later on in all calculations that we'll make, I'll take only epsilon naught. Okay. Now, to take it further, I will talk to you about neutral points. A neutral point in space is such a point at which the net electric field is equal to 0. And if at that point you bring a test charge plus Q naught, then the net force on that charge due to the distribution of charges, which gives us E net equal to 0, F net will also be equal to 0. There has to be we have to be careful, and I'll just say, it doesn't matter, but I'll just constrain myself to say that Q naught does not disturb charge distribution. Okay, so it should not disturb, which any Q naught will do. So I am trying to tell you the truth by telling you a lie, which we often do in physics. We have to depend on certain ideal conditions when lies are important. Now, when I said that E is equal to 1 upon 4 pi epsilon naught, let epsilon r be equal to 1, Q upon r square, then let me put my charge Q at the center of this spherical body. This is a toy for my grandson, Mr. Ali. Okay, courtesy his father, that I'm going to tell you. So anywhere on the surface of this sphere, all points on this sphere are equidistant from the center. Okay, at a radial distance, right? So this value, whatever I've taken over here, will be true for all the points on the surface of this sphere. Okay. Now, let us take a very simple ensemble. There are 2 points A and B, where I put 2 charges, Mr. 1 and Mr. 2. Mr. 1 is plus Q and Mr. 2 is plus NQ, where N is, I have just taken it as greater than equal to 1. Okay. So let us search as to where I'll get a neutral point at which the electric field will be equal to 0. Now suppose I take N is equal to 1. Okay, so I have plus Q here and plus Q here. Okay, and the line joining the 2 charges is bifurcated at the point O. This is the center of the line joining the two. So what I'll get, because of the charge plus Q over there, I will get an electric field which will point towards the open end of this pen. And because of this charge plus Q, I'll get this thing in this direction. Okay. The two will equal over here. This is what the guts say. Because if the point P is close to A here, then the field due to this will be larger as compared to the field due to this. And there will not be a balance of the two fields. Or if you put a charge over there, there will not be a balance between the two forces. This force will be greater than this force. If instead I shift my point P on this side, then this becomes closer and this becomes farther. So that 1 upon R square factor says that, well, Mr. Hasan, now this field due to this charge over here will be more as compared to the field due to this charge, and therefore there will be imbalance. So if we want to convert the balance, convert imbalance into balance, we will have to shift our position towards the other charge. So ultimately what happens is that at the point O, midway between the two charges, I will get a situation in which the net field will be equal to 0. Now if n is more than 1, okay, if n is more than 1, then for the same place O, the field due to this will be more as compared to the field due to this one. Okay. So there is an imbalance. So let's see which side I'll have to shift our point P in order to get the balance, in order to get the neutral point. If I shift it on this side, okay, then this field will become much larger as compared to this field. And therefore on this line here, the between O and B, there will not be a neutral point. Okay. Well, if I extend this line on this side, like this, on this side, then for every point the field due to Q will be like this, and the field due to NQ will also be like this, and therefore there will not be a balance. If you go this side, then also there shall not be any balance. But between A and O, there is a point P located at a distance, okay, x from O, okay, where a balance is possible. Let's create a balance. Let's put the value of E net is equal to 0. Therefore, the E due to Q and the E due to NQ should be equal and opposite to each other. This is evident for the calculation I have made here. The electric field, just the magnitude, okay? I'm not bothered about putting your vectors, signs, etc. just now. Okay, we should not be bothered initially. Finally we can. With practice we can do that. No problem. So EQ will be equal to 1 upon 4 pi epsilon naught Q divided by A minus X. This from here to here it is A, and from here to here it is X. So this distance becomes equal to A minus X whole square. Okay. And for this charge, E will be equal to, E NQ will be equal to 1 upon 4 pi epsilon naught NQ upon A plus X, because this is A and this is X, so P to V will become equal to A plus X whole square over here. Okay. Now the two should equal each other. And when I equate, I'm leaving that, I'm not writing here, okay? You can see for yourself that 1 upon 4, if I equate these two, then 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught, they will cancel, q and q will cancel, so what I am left with is 1 upon a minus x whole square is equal to n a plus x whole square. A is known to us, x is known to, n is known to us, and this is a simple algebraic equation, and you can calculate the value of x. There is no problem. Just numerical values are, even the algebraic values you can work out. So this is the situation when we have two like charges, plus or minus q and plus or minus nq. Okay. And the situation I have shown to you that this is point P, the two are equal to each other, so the net value is equal to 0. I hope you understand. Okay. Now two unlike charges, q and minus nq, but again I am taking n as greater than 0, or even we can take this as equal to 0, no problem. You can take otherwise, even n is less than that. So these are the two situations, A and B. Distant r apart, which is r is equal to 2a, so I take this A and take this A. Now let us see, where shall we get the neutral point? Okay, let's see if I can get between this point and this point anywhere. The answer is sorry, because if for example I take point here, just a point over here, okay, then what will happen? That because of this q, the field will be like this, and because of minus nq, the field again will be like this. So in the same direction, the two will add, algebraic addition will help us to find that this value is unbalanced. Okay. If I go on this side, on the extended side, you can again argue that because the magnitude of this charge is more and the distance is less, therefore the value of the field will be much more as compared to the value of field due to this one, which will only in this direction, and therefore there is no question that we get a neutral point. But for example, if I have a point here on this side, because q is smaller in magnitude as compared to nq, okay, in magnitude, therefore the field due to this will be something like this, okay, and the field due to this will be something like this, okay, like this, because the distance is more. So this 1 upon r square factor will tell us that it is located somewhere. In a similar fashion, if I take the distance from this point to this point as x, then the distance from this to this point will become equal to a plus x. And we can write similar equations, and because again a and n are known to us, it should be possible for us to find out the value. Okay. So this is about two charges. Three charges is a little complicated, but if on the surface I have, there is a rectangular shape, and this shape is rather not rectangular, it is square. So there are four charges, and of equal amount, q, 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 okay. These two charges will, if we take the center, then they will cancel out the effect of the fields of each other, and similarly this pair also will cancel out the field over here, and this is heavy, so I cannot hold it, okay, and therefore I put it there. So this is a square shape. Even if the shape is rectangular, this time this side is more than this side, but there is a point in between, and that is equidistant from the corner points, and if you put the same charges all over it, then at the center there is the neutral point. Well, if instead I have a rectanguloid with how many corners? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So from this end to this end, okay, if I from this end to this end, this end to this end, like that, then all these 4 lines will meet at a point. And this point, if you calculate the electric field due to equal charges put at the corners of this rectanguloid or cube or any kind of a structure that we have, then the electric field at that point due to equal charges at the corners will be zero. Similarly, if we have a hexagon has how many sides? 1, 2, 3, 4, 5, 6. And at every gone there is an opposite end, okay, and if we connect all these, then it meets at a point. At that point also it shall be equal to 0. Okay. Now what is that thing I'm talking to you about? That is the beauty of what you know and you have been trained at, and that is called the geometry. And more beautiful than geometry is what is called symmetry. The most beautiful thing in Mother Nature is symmetry. And such symmetrical geometrical structures, if they are given to us, then well, a triangle has how many sides? 3. Rectangle or square has 4. Pentagon 5. Hexagon 6. Heptagon 7. Okay, octagon 8. Like that. And each side becomes the angle that it subtends at the center of that geometrical structure becomes smaller and smaller and smaller and smaller until we arrive at what we call a circle. This is a circle. Okay. Funny question. How many sides it has? The answer is it has infinite sides. And what is the angle that it subtends at the center? The answer is the angle that it subtends is 0. Okay. So because this is a gone, like pentagon, heptagon, okay, like that, it is infinity gone, okay, infinite sides, and the angle over here will be equal to 0. But if I have this circle over here, then opposite to this point there is a point which is in the opposite direction, and it passes through, the line joining the two passes through the center. So like that. So what will happen? To the center of a circle, my dear friends, again the electric field will be equal to 0. Electric field will be equal to 0. And similarly, in the case of Mr. Ali's ball, okay, for every point on this ball, there is another point over here. Okay, and they are opposite to each other. equidistant from the center of the sphere. Equidistant from the center of the sphere. So my sphere, my ball-like thing, has a beautiful structure with the center which is equidistant for every point on the surface of the sphere, and therefore the center of it will again experience zero field. If the charge is equally distributed, and it is, if it is a sphere and the charge is put on the outer surface of the sphere, then there is a equal distribution per unit area on the surface. Okay. Similarly, on a ring that we have taken, the charge distribution is distributed equally all over the ring. So these are certain beauties that we test you, and we don't test you the calculation of electric field or calculation of a field. That's true for the case of gravitational field also. Okay. But what we find, naturally, if you take a spherical body, then inside another sphere, concentric. So this solid sphere is made up of concentric shells. You can talk about the shells, and then all the shells, they have, if the charge is distributed over there in some way and equally distributed over all those shells, then we will say the center of that spherical body, the earth, like in the case of Mother Earth, some people argue that the value of small g at the center of the earth will be equal to 0 because of these classical mechanics, but we don't know what will be there. Okay, it's for you people to think about it. Okay, so this is the neutral point. Why I took the neutral point? The calculation of the neutral point is equally valid even in case you take two wires through which the currents I1 and I2 pass, and in between you keep another wire, whether that will experience a force or not. Okay, so in Ampere's relation we make similar kind of calculation. So this is the simple, this kind of a physics is involved in all situations. It should occur to us naturally. Okay, it occurs to us naturally, and we do with that. So next item I'll talk about what is the electric field lines. So I told you that we are going to talk about electric field lines of field, and the lines of field from a positive charge, they diverge, okay, in all directions. So I've shown here, like in the other lecture, that we have lines of field which are in a situation like this. They are going in all possible directions and piercing through. So I've just taken a section, a section of this sphere which is around that particular point under consideration, and they appear to us to be diverging from a single point. I'm talking about a single point, so the field lines are diverging. Okay. So this is a spherical surface, and this subtends a solid angle at the center of the sphere, and that angle is, I'm just introducing to you, you can check for yourself, 4 pi steradians. the angle subtended by the circle, the ring at the center is equal to 2 pi radians. But this is 4 pi to radians. Okay. Now, this is one thing. The second thing is that if I consider that there is charge q, and for that charge q, n lines flux out. Then if the charge is 5q, then how many lines will surge out from it? That will be proportional to it, and therefore 5n lines. If the charge is nq, then there will be nn lines. That will be the number of lines, etc. Okay. So we do not confine a set number for a set charge. But comparatively, if we say that if there are q lines from this, then n lines for q, then n by 10 lines from q by 10. Okay, like that. So there is a kind of an element of that proportionality that exists. Here in this case, you can see that the lines are diverging, and the lines move from something high to something low. Okay, please check what thing high and what thing low. This lines concept was given by the great mind MF Michael Faraday, who fathered the concept of lines of field. Okay. Now here I write, there is another thing about the field lines, and the strength of an electric field, a magnetic field, a gravitational field, this field, that field, a me field, a you field, okay, can be measured, can be set, can be obtained by counting the number of lines fluxing out and fluxing in through delta S, which is a normal surface normal to it, small surface area normal to it, and I told you that the surface area is a vector. Okay, so a small surface area per unit area. So if that way we can define the strength of the electric field, which we have defined here as E is equal to 1 upon 4 pi epsilon naught capital Q upon R square, that can also be defined this way. Okay. I will wind up my lecture here, okay, shortly, and I will tell you that if in space we have parallel and equidistant lines like this, then in that region of space we say that the electric field, the magnetic field, and this field and that field, me field, you field will be constant. Like in the case of capacitors, we'll see that parallel lines are there and the electric field is same all over the distance between the two plates. Okay, it's the same from one end to the other end, from the positive to negative, of course. I will tell you that. I want to close my lecture with a negative note, and the negative note is this, that many a learned gentleman and fair ladies who have been teaching us through decades, they take it easy and they say that the electric or magnetic or gravitational and whatever field is an area around that electric charge, a magnetic monopole or magnetic dipole, which influences that. And by area they mean a certain volume. Ladies and gentlemen, the young scientists in the making, the potential professionals of tomorrow, the potential scientists, I beg to differ. I beg to differ in the sense that electric field, or any field for that matter, is a concept, whereas area or volume or whatever you say is well-defined thing. So I will continue from here. I'm not being disdainful. I have all the respect for those people. Okay. But to my mind it appears, why? Maybe. Anyway. So they are nice people, they have been nice people, they are nice people, there will be nice people. Okay. So my salute to all of them. Right? But I want you to know that it's nothing like the area around. That field, the area field, is a football field, a volleyball field, a field where you can play, okay? Athletics field and this and that. So don't confuse with that. That is a physical field, but this is a conceptual field. It helps us to find out and to solve very typical problems in a confident manner. So thank you very much. You will see, and I will plot the lines of field, etc. for you for a single charge, double charge, and you look at it in your text. They'll give you many things. Okay. So we'll talk further anyway about the electric field, and thank you very much.